to Math 408, L functions and sphere packings. So today we're going to do hard problems.
I always wanted to take little problems or whatever.
Oh, the little problems is a fun class. Hard problems actually has meaning in mathematics. And so you can actually quantify, especially if you're on the CS side, just how hard a problem is, how long will it take you to do it. And so you often look in terms of what are the inputs and how long will it run as a function of the inputs. So what's the simplest hard problem you can think of?
The halting problem?
That's the simplest you think of as the halting problem?
The base one. Solving an incomplete Sudoku problem.
Knapsack.
Yeah, that one's not so easy.
Okay, these are all hard problems, but I think this should be a lower level hard problem.
How many?
It's not even, we're not even sure if it's a hard problem yet. Quantum computers will handle it.
Oh, factoring.
Factoring. So this is the problem of teaching, smart college students, as you sometimes miss the earlier ones. And factoring has a really nice aspect to it. So let's say n is the product of two primes. We do not know any good way to factor n. So I'm sorry?
You can guess.
You can guess. And so let's put things in perspective. Let's say P and Q, let's say on the order of 200-digit primes. And so n will be of size 10 to the 400. How long would it take us to guess if we try all the primes we can? And what's the largest prime we need to worry about checking if n is of size 10 to the 400? 10 to the 200, because if you write it as a product of two numbers, one of them is at most square root of x. How fast is your supercomputer?
Very.
Okay, so give me how many operations a second. How many primes can it check a second?
Trillion.
Okay, trillion. So million is 10 to the 6, billion is 10 to the 9th. Trillion is 12. So we'll do 10 to the 12th.
10 to the 24th. Is that trillion or is that?
How about if I go up to 10 to the 15? A quadrillion, okay. Now, how many seconds are there in
10.
a year?
10. 3600.
There's 3,600 in an hour.
And there's 525.
Okay, did you just calculate it for us?
It's around 30 million.
Okay. I often just round up and say 100 seconds in a minute, 100 minutes in an hour. But you say 30 million? So a million is 10 to the 6. We'll call it 10 to the 7 seconds in a year. How many years has the universe been around?
20.
20 years?
Okay, I'm 21, so I only have knowledge of 21.
All right, that's a lower bound, assuming you remember things well. You want to say on the order of 10 billion years?
Yeah.
We'll bump it up to 100 billion years, and we'll always round up a little bit. So billion was 10 to the 9th, so we'll call it 10 to the 10. So this is how many things we can check from one computer running since the dawn of time. Do you know how many objects there are in the universe, roughly?
10 to the 30. Atoms? Way more.
No.
10 to the 90.
10 to the 90, 10 to the 80, 10 to the 85, depending on what you want to count things. Let's count it as, say, 10 to the 85. And let's say every object in the universe is a universe. And in every object of that universe is a supercomputer devoted exclusively to us, running since the dawn of time. So we get to square that. All right, so if we multiply this out, 85 becomes 160, 170, 180, 190, 202.
Hey!
So that would be enough to do it. So if we do two primes of size, we can do it. If we bump these up just a little bit, we're now short. To just give you a sense of how bad, just guess and check is. When a universe of universes of supercomputers running since the dawn of time is not enough to... And then, of course, the question is, how high do you need to go up? So right now, we do not have any good algorithm to factor.
Why would quantum computer be so much better?
I don't really know that much about quantum computers. It has a way in terms of how it does the calculations, in terms of looking at all the possibilities. It's, we can read up on it. But what's interesting is this problem is only hard in one direction. There's an inverse problem that's easy. What's the, right, multiplication. And this is actually quite easy. You know, given P and Q, we form P times Q. And it's not even remotely a challenge. A lot of mathematics, especially cryptography, is built around problems that are believed to be hard in one direction and easy either in the reverse or if you have some extra information. If I tell you one of the factors, it's not hard to factor if it's a product of two primes. The other thing is there's a lot of problems where it may be hard to solve, but for those of you in computer science, what might be easy? Check. So often, solving is hard, but verifying is easy. So here is one example. It is very hard to factor a number in general, but it is easy to verify. As an aside, there is a problem that's related to factoring, which is easy.
Multiplication.
Well, the inverse one, yes, but if I give you a number, it's very hard to factor it. But there is something I can tell you about n in polynomial time.
Is it checking whether it is prime?
It's checking whether or not it's prime. So, primality testing is fast. How do you think you tell if a number's prime?
By all the integers?
You divide by all the integers. So you can actually tell if some numbers are prime without factoring.
But in one direction, you can try Fermat's little theorem.
So Fermat's little theorem is not a bad approach. So you use a lowercase l to distinguish this from Fermat's last theorem. And so this basically says if the GCD of A and n equals 1, then A to the phi of n is congruent to 1 mod n. And phi of n is the cardinality of the number of 1 that's equal to m strictly less than n. I'll do less than equal to n such that m and n are relatively prime. Has anybody here not seen the Euler-Tauschend function or the phi function? Okay. I mean, you should have seen this in abstract algebra.
Which I haven't taken.
Neither have I, but I've taught it, but have not taken it.
Well, I haven't taught it, nor have I taken it.
All right, so you should teach abstract algebra.
Exactly. So what?
So what would be a good choice of n? What kind of number?
Prime.
Prime. So if n equals p is prime, phi of p is just p minus 1, and that implies a to the p minus 1 is congruent to 1 mod p. So, for example, let's take n equals 6, and I need a number relatively prime to 6.
5.
5. And so we're going to prove 6 is composite in a very painful way. Okay? So let's compute 5 to the, I'll write it as a to the n minus 1, which is 5 to the 6 minus 1, which is 5 to the 5. So this is going to be 25 times 25 times 5. But we're looking at this mod 6, right? So what is 25 mod 6? It's 1 because 6 times 4 is 24, so this is just 5. So 6 is composite. And so Fermat's last theorem, which basically is Lagrange's theorem, that if you take a subgroup of a group, the order of the subgroup divides the group. It's basically related to that. We now know 6 is composite. If I'm telling you a number is composite, what do you expect I would be telling you? It's factors. And so unfortunately, this does not give you any of the factors of 6. It just tells you that 6 is composite. Now, in general, if I take n to be a 200-digit number, is it going to be practical to raise raise a to a 10 to the 200? I'm sorry?
Yeah, with modulo, it's composite.
But even with modulo, we can't do 10 to the 200 operations.
You can like divide and conquer.
How do you do divide and conquer?
Square it, multiply, square it, multiply.
Good. So we use repeated squaring. So did we cover repeated squaring?
I didn't see us.
I'll do it really fast. So repeated squaring, we can write 100 base 2 as 64 plus 32 plus 4. And if we want to calculate x to the 100, x times x is x squared times x squared is x to the 4th, x to the 4th times x to the 4th is x to the 8th, x to the 8th, x to the 8th is x to the 16, x to the 16, x to the 16 is x to the 32, x to the 32, x to the 32 is x to the 64, and then we just take this, multiply by this, and multiply by this. And so rather than having to do something 100 times, we do it basically at most like twice log 100. And so the number of steps, if you want to do x to the n, number of steps is at most like 2 log of n base 2. If you're worried about storage space, what you can do is you can always just keep storing this, and you initially start off by storing 1, and then every time you have something that's a factor, you keep it. So we start off by, we store 1 in x. We don't want to keep x squared, so we keep it as 1, and now we have x squared. Now we go up to x to the 4th, we keep x to the 4th, x to the 8th, x to the 4th, x to the 16th, x to the 20th, x to the 32nd. And when you do it like this, you can...
We want to keep it 16.
Oh, sorry, we're not keeping 16, sorry. 36, thank you. And when you do it like this, you can keep your storage costs down as well. But the number of operations you need to do is only on order log n. So this is a classic problem that is thought to be hard in one direction and is very easy in the other. So what other problems have you seen that are hard one way and easy another? Or at least hard to solve, but easy to verify. Yes?
Roots of a quintic.
Roots of a quintic. That's an interesting one.
Is it easy to verify?
So what kind of roots are you talking about?
The zeros.
Well, what I'm saying, are the roots integer roots, rational roots?
Oh.
Because we don't have a general closed form expression for the roots of a polynomial of degree 5 and higher. So if you could start off with the roots, construct the polynomial, and if you don't have the formula for the quintic.
This was verifying, it's easier.
Oh, okay, just verifying.
Yeah.
Yes. So finding roots, checking to see if something is a root, yes. And in fact, the story is that in the old days, you could challenge, mathematicians could challenge each other, and the person who came up with the formula for the cubic kept that formula in strategic reserve. So that whenever somebody challenged him, he basically said, here's my problems, here's 10 cubics, find the roots.
It was like some Italian guy.
There's Tartaglia, and then there's Cardano, who comes afterwards.
I remember someone in our real class gave a 1-minute lecture on this.
No, and once you have the formula, it's a nice formula. And you can ask, well, why does the method not generalize higher? And there's a nice argument where you have this associated quantity, and the quantity has lower degree, which is good because then it reduces it to a polynomial of low degree and you can solve. But once you get to a quintic, you unfortunately have something that comes up with a higher degree, and so the method makes things worse. As an aside, I will risk putting this up there. You will probably remember exactly which student I am talking about. Do you know already from that? Okay. He lost many, many, many hours over the years trying to solve this because it's a guaranteed A+ in any of my classes. Do you know the student now? Yes, you do. So you know it was many hours.
Yes.
So here is a proof of the irrationality of square root of 2. And this is a geometric proof due to Tenenbaum. Stanley Tenenbaum. So imagine the square root of 2 is a over b, and without loss of generality, we can assume a and b are relatively prime. So if we do something like this, b, b, a minus b, a minus b, we have 2b squared is a squared. We've double counted this region, and we haven't counted these regions at all. So that tells us, and again, not to scale, that this area plus that area equals that area. So twice a minus b squared. Now what's the side length here? It's, if you take a, b, so if you take a minus b minus a minus b, so it's going to be a minus 2 a minus b. Yes? So now you get 2 a minus b squared. You'll get 2b minus a squared. And so you get 2 is 2b minus a over a minus b. Like that. Okay? So I'm going to change what I did over here. Normally when you do this proof, we normally say a and b are relatively prime. And we get a contradiction from that by finding something that has a common factor. What I'm going to do instead is, rather than say they're relatively prime, I'm going to assume b is the smallest that works. We're assuming the square root of 2 is rational, so there has to be some representation. If there's many representations, choose the one that has the smallest b. Well, once you find something that works, say b equals 17, you only have 16 other candidates to check. So it's well defined that you can find a smallest. So all we have to do now is show that a minus b is less than b. If a minus b is greater than or equal to b, then a is greater than or equal to 2b. So a over b squared is greater than or equal to 4. So this proves that the square root of 2 is irrational. Okay? The reason I wanted to show you this is it actually goes along the lines of what you said about trying to solve the cubic. So the extra credit, it's an A+ in any class with me, is to prove that the cube root of 2 is irrational with a geometric construction. I will give an A+ in any of my classes for that proof.
What makes it so hard?
Play with it. The
Isn't
geometry
this-
is much worse.
Isn't this one,
I'm sorry?
the Tannenbaum one,
Yes?
how is that not geometric? Cube root two.
Cube root of 2.
Oh. Okay.
So I first saw this at a colloquium. I gotta be very careful because this is being recorded. What are you supposed to do in a math colloquium as a student or professor?
Ask questions.
Ask questions, but
Don't talk.
don't talk. Your full attention should be on the speaker. Professor Morgan might have asked me during the colloquium, or might have commented to me during the colloquium after we saw this, that that's a beautiful proof. It's a shame it only works for square root of 2. After the colloquium ended, I might have passed a napkin to him, which had a proof for the square root of 3. And again, terribly not drawn to scale, but you'll have triple counted. You can extend this to do other triangular numbers. And so the first triangle number goes 1. What's the next triangle number? 3. Next?
11?
6.
6,
10. So we can actually prove that these numbers have irrational square roots. Do you think every triangle number has an irrational square root? So Tn is n plus 1 over 2.
Yeah.
So what comes after 10? 15. Notice, look, we're adding 2, 3, 4. You just add another row of dots. After 15 comes
28, 36.
So what's interesting is when we proved this, we knew that something would go wrong later, that it worked in the beginning, but we knew there had to be an obstruction down the road, which was really interesting. That eventually we won't be able to get something statement like the denominator is actually smaller than the previous. But it was weird knowing that as we were doing the calculation, it would not work all the way, that there would be some problem. And in the approaches that solve the cubic or the quartic, what they often do is they find some related polynomials and they try to reduce degree. And if you have something that reduces degree, then you can eventually reduce it down and hopefully you get down to a quadratic or linear, which we know how to solve. And when you start off with the quintic, the associated polynomial has a higher degree and you're just out of luck. It's something very similar here. How many of you know about the Hamilton cycle problem? So what is the Hamilton cycle? Good. And so you have a graph, and you can get from one vertex to every other vertex going through each segment once and only once. So this one is clearly going to fail. Do you know any results that must be true if you want it to succeed?
You can't have more than 2 nodes of degree greater than less than 2.
Good. So if we have if we have a nice graph and we have something that has only one thing coming out of it, that could be either the start or the end. We can have another one like that. So basically, you need to have at least 2 edges coming out of every node, except possibly 2. And the question becomes, if I give you a graph, can you find a Hamilton cycle on it? This is hard. What's easy?
Is this cycle a Hamilton?
Yeah, is this cycle a Hamilton cycle? All you have to do is then just go through and check and see, did you hit each vertex once and only once? There is a lot of math problems I have on a riddles page that I maintain, and one of them is you are supposed to divide a triangle up and get 10 triangles. And it's amazing how many solutions I get which don't have 10 triangles. It's like, you can just count. You can count. That shape here is a quadrilateral. It's not a triangle. And so sometimes it is a bit hard to check. I think the figure, I think this is the figure. And you add 2 lines, and you now have 10 triangles.
You not have other shapes?
Yes. So right now there's only 5. So we do not count this big one over here as a triangle because it has lines in it. So to count as a triangle, it can't have any internal lines. So if I go like this is now a triangle over here. This is a triangle over here. This is a triangle over here. These ones are not triangles. But I have another line, and if I go like this, I get a triangle over here, one over, no, I don't get one over there, I get one over here. And you can see this is a clearly bad choice of 2 lines. But it's amazing how many solutions I have that do not have 10 triangles in it, that they do accidentally count something that's a quadrilateral. Just because you think something might be easy to check does not mean it is easy to check.
Well, it's so easy to check.
Yeah, okay, it may not be easy for all the people in the conversation to check. Why am I bringing this up over here? So one of our homework problems, was it the one that was due today on counting short vectors, counting lattice points?
Yeah.
This could be a hard problem. So the shortest vector in a lattice. And so I give you, say, a basis. So V1, V2. We then have an associated lattice, which will be the set of all M1, V1 plus M2, V2, Mi's and Z. And so how would you find the shortest vector? So the first question is, can the shortest vector be arbitrarily small? So we'll assume, without loss of generality, what's the length of V1?
1.
And the length of V2?
Greater than 1.
Greater than or equal to 1. So we can normalize like that. And the question is, how small could the smallest vector be? So can you give me a choice of V1, V2 where you can get a vector smaller than epsilon?
Yeah.
Okay. How would you do that?
Well, so if you have V1 is just the vector 1, 0.
I like it.
Yeah. And then V2 is the vector like 1 and then like epsilon over 2.
Okay. So not to scale. 1, 0, and 1. You said epsilon over 2?
Yeah. So
Not,
just something that's very small.
right, but you don't want to do epsilon?
Oh yeah, we can also do epsilon.
Okay.
You don't have to be too small.
I mean, that's true. Epsilon over 2 is half the size of epsilon, so it is a smaller vector.
Then, because of the lattice, we know that there's a point at like -1. I mean, yeah, -1, 0. And then if you take the V2.
All right, so now we go to -1, 0.
Yeah, and then take V2 from there.
and then we add v2.
Then we're like epsilon away from.
So now this will be 0 epsilon. And so we have this vector over here. Do we know that we have this vector over here as well? Because if two vectors are in the lattice, so is their difference. So we would also know that we have it over here. So what you did is perfectly fine, but we actually have multiple ways of getting something like that. So this shows that I cannot really have an interesting problem if all I give you is the length of the vectors. I could make this vector have length 1 and not 1 over epsilon, and then just be at a small angle. And then I could have things very small as well. So we can make the smallest vector as small as we want for any two vectors. So if I give you what the vectors are, somehow we need to use information about that to figure out what the smallest one is. Or can we at least get bounds? Can you bound upper, lower, the length of smallest vector? You guys do one direction, I'll do the other.
We can do an upper bound.
Okay,
One.
good. Upper bound of V1. And in fact, we don't even care for the upper bound if V1 is the smallest one or not. So the upper bound is not a problem. Can you give me a lower bound for the length of the smallest vector? So we may not be able to solve it, yes.
Can we assume without loss of generality that V1 is 1?
Without loss of generality, we can always assume V1 is 1, because otherwise we just rescale things. And without loss of generality, because my artwork sucks, what do we assume about V1?
1, 0.
It's 1, 0. So, you know, make our life easy. All right, so my first vector here's V1, which is 1, 0. And V2 has length at least 1. And so without loss of generality, we've talked about, I think we can assume V2 is in the upper right quadrant. Worst case scenario, you can always just multiply this by -1, put them both in here, then multiply them both by -1. There is a circle of radius 1. And here's V2. So what can you give me? What parameter do you think might play a role in the bound?
The imaginary part of the.
So one is the angle, the imaginary part, the projection upwards. So what is the lower bound that you, I'm sorry, what is the lower bound you can give me? So if we have our smallest vector, I can write it as, you know, m1 v1 plus m2 v2 for some m's and v. Right? So can you give me a lower bound on L for its length?
So can be the difference between the two, or one?
What do you mean by the difference between them?
Like V0 minus.
So that whole large vector, potentially?
You could draw it to have it smaller. Like one, I think.
But for instance, if the two vectors are perpendicular like this, if I look at their difference,
Exactly.
it's actually going to be bigger.
But if the minimum of that and one.
So you could do minimum of that. But is that going to be a lower bound?
Is it sine times the length of V2?
Ah.
Yeah. I think
So what you're doing is you're writing V2
complex vector.
as cosine theta times the length of V2, 1, 0, right?
Yeah.
Plus the sine of theta, the length of V2, 0, 1.
Yeah.
So now if we look at adding them, L would be some number of copies of V1 plus some number of copies of V2. So it would be M1 plus M2 cosine theta length of V2 as the first component. And the second component would be M2 sine theta length of V2. Therefore, the length of L has to be at least sine theta times the length of V2. Yes?
Here we're assuming M2 is non-zero.
Right. And if M2 was 0,
Then more. The minimum is just M1.
right. So this is M2 does not equal 0, and then the length of L would be greater than or equal to the length of V1 if M2 does equal 0. So do we now have a lower bound for the smallest vector in our lattice? Yeah. And as the angle theta gets closer and closer to 0, which is very similar to the example that was given earlier, then we can get a shorter and shorter vector. So it's not hard to get bounds. And for a lot of problems, this is unfortunately how it is. To get bounds, to get an area where you need to look, it's not so bad. But to actually find the smallest vector can be a real challenge. Now, if we think about this, can we make this into a proof?
Yes.
Okay, how?
By doing it. The proof is that we can put a lower bound on the smallest vector.
But I want to, so every one of these is a vector in the lattice. So all of these live in our lattice. But I want to find the one that has the smallest length. So the length of L, so I am going to do the standard algebra trick and study the square of the length rather than the length. You have hopefully seen this in countless classes. Why do we do this?
Dot product.
Not dot product. We don't like the
Always positive, not negative.
well, I mean, the length is not going to be negative. So why do I study the length squared?
No square root.
No square roots, right? We don't want any square roots. We want to avoid square roots as much as possible. And so by squaring things and looking at the length squared, we don't have the painful square root. So this is going to be m1 plus m2. Let's call that alpha. Let's call that beta. These are just fixed numbers. m1 plus m2 alpha squared plus m2 beta squared. So if you want, we can call this L of m1, m2. To to just remind us that it's coming from the choice of M1 and M2. Is this hard now to find the M1 and M2 that lead to the smallest vector? So there's a little bit of informality that has been going on all day. I hope you will excuse the informality. I don't think anybody was confused in what I was doing. But the problem, if you be very specific about the language I'm using, we're not really doing what we're supposed to be doing. And this was inspired by the conversation that happened before class today. I wanted to work this in. We were talking about Casablanca. And Casablanca is famous for one of the most famous lines in movie history. What is that line? I'm sorry, no, we won't always have Paris.
Play it again, Sam.
Play it again, Sam, which is never said in the movie. Variants of play it again, Sam are said, but the line play it again, Sam is never said. I'm asking you to find the vector of smallest length in the lattice. Technically, what is that?
0.
It's technically the 0 vector. So when we talk about this, we really mean the smallest non-zero. My math book freshman year had a wonderful sentence where it said, you know, sometimes the empty vector space causes problems, so we just exclude it whenever that would happen without saying so. We really want to find the smallest non-zero vector. So find M1, M2 not equal to 0, 0 that minimizes the length of L M1, M2 squared. Is this a hard problem?
In the computer, sort of.
Well, you can break it up into a couple of cases. If M1 equals 0, is it easy? In this case, what would you do?
M2 equals 1.
Yeah, in this case, M2 equals plus or minus 1. If M2 equals 0, M1 equals plus or minus 1. But you know, again, it's the thought process here as to how you would do it. Break it up into cases, break it up into cases. Now, both of them are non-zero. Without loss of generality, we can assume M1 is greater than or equal to 1. Because we can always replace M1, M2 with negative M1, negative M2. So without loss of generality, M1 is greater than or equal to 0. And now,
Wait, 0.
it's greater than or equal to 1. So now we know M1 is greater than or equal to 1. M2 is not 0. So we can even break it up into subcases if you want. A, M2 is greater than or equal to 1, and B, M2 is less than or equal to negative 1. How would we handle those cases? Yes?
We assume that it's in the first quadrant, B2.
We can assume that if we want B2 is in the first quadrant.
Well, M2, like case A where M2 is greater than 1, that is done. This doesn't work because it's going to be less than or equal to. It's going to be greater than if M2 is 0 because alpha and beta are positive.
Good. So we know in this case, we've just added more.
Yeah.
So we can eliminate this case.
This kind of looks like a Euclidean algorithm kind of thing here.
Yeah.
Now, where
Why can't I just use calculus to find the values of m1 and m2?
They're integers.
They're integers. No calculus as discrete. So there's a nice problem that you might have seen, the knapsack problem.
Is this?
Have you done this in CS? So you have a knapsack, and you have, maybe it can take 150 kilograms. And you have three objects. This object weighs 51 kilograms, and it's worth $100. This object weighs 51 kilograms and is worth $98. And this object weighs 50 kilograms and is worth, let's see, $80.
This one does not seem like the hardest. No?
This is not a hard problem. So imagine you can take as much as you want of each one. And for every 51 kilograms, you get $100. How would you fill your bag?
350. Yeah, 3.
No, but you don't have to take a whole unit. You can take parts of a unit. For every 51 kilograms, you get $100. Here, for every 50 kilograms, you get $80.
We can take parts of it, then we just figure out which one has the best rate.
Right, so which one has the best? Oh, which one of these do we not care about?
2.
2 is stupid. Right? It's the same weight as 1, but not as valuable.
And if the rate's constant, then we know one's the best.
1 is the best because you get $20 extra over the 80 for just 1 kilogram. That's a terrific rate. So in the continuous case, you would take all from 1. In the discrete case, you would take 3 copies here. If you have to take an entire thing. The problem about this is that the integer optimal is nowhere near the real optimal. And there are times when the integer and the real optimal are close to each other. But unfortunately, what this means is that if you have techniques that work to find real optimals, they will not necessarily find integer optimals. But we do have, this expression over here. So what I want you to think about for class next time is, are you able to use this and find the smallest non-zero vector?
I mean, you can bound M2.
So you can bound, but can you actually find the smallest vector from what I've given you? And so we will report back on that on Monday. Have a great weekend.